All right, let's see. We're going to use the divergence test, an integral test, to determine the divergence or convergence of specific series. So let's find out what we've got going on up in here. We've seen some ways that a series can converge or diverge. Can you think of a way to simply look at a given series and know that that series converges and diverges? Well, no. And let's see, consider this sum. What can you tell me about it? How can we use something you know how to do to tell me if we converge or diverge? Well, if I look at this, this reminds me, oh, it reminds you, reminds me of this. They kind of look similar, because we talked about that when we talked about improper integrals. And when we did that, okay, so what we said is we said the limit as b goes to infinity, 1 to b, 1 over x dx. So that's the natural log of x. Ooh, I forgot the limit, sorry. The limit as b goes to infinity of the natural log of x from 1 to b, which is the limit as b goes to infinity of the natural log of b minus the natural log of 1. Natural log of 1 is 0, but the natural log of b, as b gets huge, that goes to infinity. So this integral diverges. Well, this is going to be similar to that. Fewer, quote, fewer points, but similar. So I'm gonna conjecture that this diverges. Because this integral diverges, so I'm going to guess that the series associated with it also diverges. All right, so for this one, if I think about the integral, so the integral 1 over k squared, nope, change it to x's because we're doing integration, silly pants, x squared dx. That's from 1, I'm going to call it b right away, so I put a limit in front. B goes to infinity. So that's going to be the limit as b goes to infinity, negative 1 over x from 1 to b, which is the limit as b goes to infinity of negative 1 over b minus negative 1. 1 over b as b goes to infinity, 1 over b goes to 0. So add 1 to that and you get 1. So this integral converges. I'm going to claim, I don't know if this is true yet, I'm going to claim that this series also converges. And let's look at that next one. All right, it says, why did I have to change that? So k equals 2. Well, before I had k equals 1. What's wrong with k equals 1? If I have 1 over 1 square root natural log of, what's the natural log of 1? The natural log of 1 is 0. Square root of 0 is 0, so that's 1 over 0, so that's a ruh-roh. So we don't want to do that. Or ruh-roh. Let's think of this as integration, though. So we've got the, I'm going to jump right to the limit. Limit as b goes to infinity, integral 1 to b, 1 over x square root ln x dx. Well, I know how I look at that, but I bet you don't look at it that way. So I'm going to show you how I look at that. Maybe it'll help. So I look at that as 1 over x, 1 over the square root of the natural log of x. And the reason I look at it like that is because, let's make that my u. And that means my du is 1 over x, which means that dx is x du. Boom, I shrunk everything. That was like magic, huh? And so then I can say, okay, I'm going to write this out. 1 over x, ignore the numbers for now because I don't want to deal with that messiness. And then x du, those x's will cancel. Bye. So that's 1 over root u. So I can rewrite that as u to the negative 1/2 du. If I evaluate that, that's going to be u to the 1/2 with a 2, theoretically plus c because I got rid of the numbers. And now let's go back to x's. So this is an example where I think I would not change the bounds because I find that confusing. You can totally change the bounds, but I think I would not because it confuses me. So we've got 2u was the natural log of x to the 1/2. Evaluate that at 1 and b, which is the limit as b goes to infinity of 2 natural log of b to the 1/2 minus 2 natural log of 1 to the 0, because the natural log of 1 is 0. All right, so the natural log of b, I know the natural log of b keeps growing. If I look at the natural log of b and then I raise it to the 1/2, well, 1/2 means square root. So if I do the natural log, the square root of the natural log, that's going to keep growing, but like super slowly. But it's still going to keep growing. So if I plug in like 49 billion, that's still going to keep getting bigger. So that's going to equal, I was trying to write equals with an eraser. Maybe not equals infinity, maybe that's bad. Maybe I'll say that goes to infinity. And therefore the integral is going to diverge. So again, my claim is that this is going to diverge also. The series is going to diverge because the integral did. Because they look kind of alike. I don't know if this is true yet, but that's my claim. Ooh, the integral test. All right. So the integral test says, if we have a function that's continuous, positive, and decreasing, and we can write it so that it kind of looks the same as a series, then the series and the integral either both converge or oh, so that's what I was doing. So this is a little bit confusing, but what this is saying is, essentially, if I can rewrite the sequence as a function, and we'd like this continuous, positive, and decreasing thing, but if I can write this sequence, ak, as a function, a of x, and then I can evaluate the integral, that will help me figure out what the series is going to do. And if the integral diverges, the series will diverge. If the integral converges, this series will converge. So my thinking that I was doing on the previous pages was correct. If I can rewrite that sequence as some sort of function, again, that function should be continuous, positive, and decreasing, then we can figure this out. All right, now we're going to use the integral test to see when the series converges or diverges. So what you should do is you should take a minute, and by a minute, probably more than a minute, but set up these integrals and see what you get. Actually, I think I'm going to do this. I'm pausing because I'm not quite sure. I think I will do a few of them. Now I'll do them all. I'm feeling generous. I'll do them all. Let me letter them so that I can make my life easier. A, B, C, D, E. And then I'm going to shrink them. So for A, again, I hope you paused. So for A, I'm going to look at the limit as b goes to infinity, 1 to b, n to, no, x to the negative 1.2, dx, which is going to be the limit as b goes to infinity of x to the negative 0.2 from 1 to b. And my argument's going to be, that's going to be 1 over b to the 0.2 minus 1. So that's going to be, sorry, this is wrong, not x to the negative 0.2. It's going to be negative 1 over 0.2, which I could rewrite, I know. So this is going to spit out 1 over 0.2. That's my argument. So that one converges. I'm going to check it off if it converges. For b, n equals, nope, just jump to the integral, silly. I'm going to integrate, so the limit as b goes to infinity, 1 to b, n's, nope, x, silly, x squared dx, oh goodness, the limit as b goes to infinity of x cubed 1/3, 1 to b, that's going to blow up, so that one diverges. I'm going to exit if it diverges. For part C, it is to the negative 0.2, so that's going to change this. So for part C, do it to the 0.2, so that's going to be the 0.8, 1 over 0.8. I know I can rewrite that. That's going to be b to the 0.8. That's going to keep growing, so that's going to go to infinity, so that's going to converge. If I do this to the 5th, so the same idea, raise this to the 5th, so now we're d to the 5th. That's going to be, by the 5th I mean negative 5th, sorry, negative 4th, which is negative 1/4. So that's going to be 1 over b to the 4th. That's going to go to 0, so that's going to be minus negative 1/4, so 1/4. So that will converge. And then the 0.98, oh, the 0.98. So for E, if I raise it to the negative 0.98, E, negative 0.98, if I add 1 to that, it's 0.02, 1 over 0.02. So that's b to the 0.02, so that's going to keep growing and growing and growing, so that's going to diverge. Now, I'm going to guess I'm supposed to make some sort of conclusion here about what's going on. So pay attention to the numbers. Think my hint to you is going to be geometric series. And there might be some sort of relationship here. I don't know if that geometric series idea is the best hint. My hint is, yeah, I guess that kind of makes some sense. But not necessarily geometric, maybe. But think about that number. Here we go. I was right. So, if p is greater than 1, then we get a convergence. So the p was greater than 1 in like the 1 over n to the 5th, 1 over n to the 1.2. Those converged. P equals 1, so that was the 1 over n, or 1 over k. Then we diverge. So we showed that using that integral test idea. And then if p is less than 1, so that was 1 over k to the 0.98, 1 over k to the negative 2, those ones diverged. That's what that p, so this is the p series test. P series test. What tests do we have so far? Well, we have the geometric series test. Geometric series test. We have the integral test. And we have the P series test. And there's one test that we haven't talked about, but I want to have talked about. So what that test says, it's called the divergence test. Now, if you think back to the integral test said that the series had to be decreasing to 0. Basically is what that thing said. The p-series test said that the 1 over n to the had to be a greater than 1 number there. The geometric series test is a useful one, I think. The geometric series test, that one said we would converge if r is less than 1. If r is bigger than 1, like 5/4 to the n or k or whatever letter we're going to use, n equals 1 to infinity, that one diverges. That helps me kind of explain the divergence test. So the first test you actually want to run is called the divergence test. And what the divergence test says is, think about that sequence. What has to be true about that sequence? And I don't know that I've formally stated this. What has to be true about that sequence in order for us to have any discussion of convergence? Any discussion at all? Well, it's not that the sequence has to converge. Because, for example, we had one that was 1 plus 1 over k. K equals 1 to infinity. That's not going to converge. In fact, even that wouldn't converge. Because we have the 1 there. If we keep adding 1, like the limit of this as k goes to infinity is 1, and so at the very least we're adding 1 to everything. So everything's going to be getting pretty big. So the divergence test says if this is, what do you think the number is? 0, then we have a chance at being a convergent series. So the divergence test says if that doesn't go to 0, then the series does not converge. So that's actually the first test I would use. So the divergence test says if the sequence does not go to 0, then the series will diverge. Automatically, done, don't have to do any more work. If the sequence does not go to 0, then the series will diverge. Done. The geometric series test says if the absolute value of that common ratio is less than 1, then the series will converge, otherwise we diverge. The integral test says if the integral converges, the series converges. If the integral diverges, the series diverges. The p-series test says if we have that p-value, 1 over n to the p or k to the p, if p is greater than 1, we converge. If p is less than or equal to 1, we diverge. It's important to note, thus far, we've talked about these 4 tests. The first test, the divergence test, is a test of divergence. The other 3 tests are tests of convergence. They can tell us about divergence also, but they're tests of convergence. So those tests we can use to show that a series converges. The divergence test we cannot use to show that a series converges. It is called the divergence test. So make sure you keep that in mind.